engineering stuff in terms of turbine and pen stuff design, and I was responsible for the electrical engineering aspect. So some of the efforts that we did, we funded the construction for a new powerhouse, new foundation, and we installed a new turbine. Those pictures show the chicken was helping us out with installing the turbine. The foundation was being laid down. Once we finished with those, we started to work on the electrical system issues. So the system had no electromechanical controls. It was running at full power all the time. So in an electrical system, when you're not matching the supply and demand, the generator tends to be under stress. And I'll cover that in a bit. So just to give you an example of what some of the procedures that the locals were doing to stop the system, sometimes they would just insert a rod into the pulleys, and the system was still running. So the turbine is under a lot of stress, and practically nothing was designed properly, or at least was not maintained properly. So going back to the electrical energy balance issue, if supply is greater than the demand, the generator tends to speed up. And if the supply is less than the demand, the generator would actually slow down a bit. So to match those two issues, there's usually two approaches: electromechanical controls, where we actually control the amount of water flowing into the turbine. So we would either decrease the amount or increase the amount according to the energy that we need. And the other approach is to actually use an electrical load controller, where we divert the excess energy in the system into a heating load. So we're basically trying to get rid of the excess power that's in the system. So the proposed controller was, we needed it to match the electric supply and demand. We did that by monitoring the frequency of the generator to know if it's actually speeding up or slowing down. And then we would divert the excess power into those heating loads. So we implemented the controller using a programmable logic controller, which is about this size. So like I said, we monitored the generator frequency. If it's over 60.5 Hertz, that means we have an excess energy in the system. So we increment what we call the dump load. Okay? And we do the steps in 1.5 kilowatts. So we start at 0, go 1.5, then 3, then 4.5, and so on. And we keep monitoring the frequency. And once the frequency dips down to 59.5, we actually reduce the dump load. So if it was 3 kilowatts, it goes down to 1.5 kilowatts. So to test our controller, we actually constructed this emulator in the lab. So the variable frequency drive and a 10 horsepower motor simulate the turbine. So that motor is driving the generator, which is rated at 13.5 kilowatts 3-phase. But because we were connecting it with a single-phase system, it was actually a 7.5 single-phase generator. So the VFD and the motor model the turbine, they drive the generator, and the generator is feeding the loads. And we have 3 meters, we're monitoring voltage, frequency, and current. So to go in more details on the controls and electrical connections, this is the layout of the system. So we have the generator, we have a current meter that lets us know how much current the generator is giving as an output. We have 2 circuit breakers, each one rated at 25 amps. So for circuit 1, we have 3 1.5 kilowatt loads. Each have their own power relay, which is controlled by the PLC. So the PLC will monitor the frequency, gives the signal to these power relays to close and effectively connect the load to the system. We always had a 2 kilowatt base load just to keep the system loaded at all times. and we implemented this setup in the figure to the right. So the PLC is on the bottom. It's that gray system. So the power relays, the 4 power relays are on top, and then we have the fuses and the protection system. And the figure on the top shows the heating elements. So there were 3 1.5 kilowatt heating elements, 1 4.5 kilowatt, and the 2 kilowatt base load. So some of the results, just to make sure that the generator is running properly, this is the voltage output of the generator. It's a sinusoidal wave with 380 volts peak to peak, which was expected. So once we run the system with only the 2 kilowatt base load connected, we monitor the frequency. The frequency actually shows that it's 60.8. That means the generator is underloaded, so we need to increase the dump load that we have. So the PLC automatically engages and slowly adds increments the dump load. So once we jump up to 3 kilowatts, we actually see that the frequency went down to 60.6. So at this point we have 5 kilowatts of total load, and the frequency actually went down. But the PLC sees that the frequency is still beyond 60.5, so it again increments. So once we hit 6.5 total load, the frequency actually stabilizes at 60.1. So the system actually operated exactly the way we wanted it to. It's in this region between 59.5 Hertz and 60.5 Hertz. So just to cover some of the advantages and disadvantages of this system, PLCs are usually easy to implement and program. We use a graphical software, ladder diagram, to actually program the PLC. The major advantage of PLCs is that they are made for industrial applications, so they can withstand harsh environments such as humidity, dust, so they can operate really well in such a system. And also they do not require power electronic switches that can inject harmonics in the system, because power electronic switches would require very high frequency in switching, and that would cause harmonics in the system. And however, this system's main disadvantage is that it toggles the loads on and off. So usually when we add suddenly a 1.5 kilowatt load to an electric system, we could see those power transients. So that was the main disadvantages. So to wrap up, in conclusion, we actually proposed and implemented a PLC system, and to test that system we had constructed a laboratory emulator. So the experiments verified that the proposed controller actually was effective in terms of keeping the generator loaded and reducing the stress on the generator. It's a viable option because of its simplicity and its robustness in harsh operating conditions. And just to conclude, unfortunately, the rehabilitation efforts now are on hold because in 2012 a large typhoon swept into the area, destroyed a large component of the forebay tank and the penstock. So unfortunately the system now is completely on hold. There's no funding in terms of actually constructing that civil work again. That's it. Thank you.
Questions, please?
Yes. Thank you so much for the presentation. What type of PLC you use and why? And is this PLC suitable in the environment you described in this place?
Well, we use the Allen Brady PLC. It's Allen Brady PLC. It's actually suitable for this environment because, as we saw in some of the pictures, eventually the system will fall apart. And I visited some systems where water is splashing everywhere. There's a lot of dust. The system is not properly maintained. So we want to make sure that we use a system that actually can operate under those conditions. and usually PLCs come with a rating. It's different rating, so we can have a PLC with high enough rating to withstand actually, you know, direct water splashes or high dust and so on.
You said that you started the project was started 5 years ago, or you became involved 5 years ago?
Well, I became 5 years ago, and we did the work in about 2 or 3 months.
Okay, so how long did it exist before that? The original design?
The original system, it started in 2004, and I think they finished it in 2005.
So there was a period where people actually benefited from the hydroelectric power.
Yeah, well, actually, the community really wanted it to stay working, so they were doing everything they could to actually try to maintain the system. Unfortunately, they didn't have the technical skills.
Right.
So they were trying to stabilize the turbine. They just put more logs and stones on it. So if they had maybe some technical help or some extra funding, they could have kept the system running properly.
So if someone were to go to any community, that one or any other one, having a system that's installed, what would be your advice to the installers?
Working with the community?
Yeah.
Be very mindful of the setting you're working in. A lot of the systems are designed, let's say, in developed world, where we assume that maintenance will happen 3 or 4 months. In those settings, it's not that they don't want to maintain; they just don't know how, and they don't know money. They don't have money to do the maintenance. So the system actually needs to be very, very basic and very, very robust. And actually, the most successful system that I saw in the area was designed by local faculty in Bangkok State University, where they pretty much used the simplest approach possible to microhydro. So the system was designed in a welding shop. They looked for the most robust generator that they could find, and they made it as simple as possible. Instead of making it look, pretty for pictures, it was just the most basic thing. And actually, it was the best operating system. So it lasted for 10 years.
So it was more, that design was more focused on function than looks.
Exactly.
That was good. How, what would you say to the humanitarian community about using hydroelectric power for the developed world?
Well, that's the thing. If we're looking for giving lights to communities, this technology is an overkill. But if we're looking to actually stir up the local economy in terms of supplying a constant electric source, because those systems usually can run 300, 325 days a year. So if we're looking to supply a stable amount of electric power that's consistent, that could maybe stir up some activity that's substantial and income generating activity, then this is a very good option. But if we're addressing only lighting and some basic needs, this is an overkill, which is actually what I saw in the Philippines. The goal was to supply lights, and this system was just an incredible overkill. So solar lights are enough.
Right.
Do you know about other regions there that there is the same system and need help? Do you know other regions? Can we in Brazil work with them? You know?
If I remember correctly, there were 15 sites that were constructed. 15 because it went through microhydro in that region went through a phase where everybody wanted to do it. That was early 2000. So there were 15 sites were constructed. When I visited, when I visited in 2010, one was running. All of them were completely worn out.
Oh?
Yes, so none of them were working except the one designed by Bangkok State University. Because the system, like I said, it's demanding on the components that the turbine, the generator, and the transmission lines. It's demanding. It needs a lot of maintenance. So So when the maintenance was falling short, the system would just each system kept falling apart. And at the moment, I'm not sure if there's any effort to actually construct new sites. If that answers your question.
Well, I have a question.
Mhm.
You mentioned that this system was overkill, but the community was very anxious to get it back online.
Mhm.
There seems to be a disconnect. Can you explain?
Yes. So the community was anxious to bring it back online for lights. So they looked at it as the only solution they had for lights. So they were spending a lot of their funds on a system that does not give them enough light. So, for example, if they use that funds to bring in solar lights, just because specifically they're looking for lights, you know. So if they bring in solar lights, that would have been a better investment for a community as a whole, instead of diverting. You know, $100 is not a lot, but it takes them about 6 months to gather it from the community. Even changing the belt, which is around $5, the system would shut down for 5 or 6 days just for somebody to, you know, walk around the community like, please give us 5 pesos, 10 pesos. So, in terms of the goal of having lights, it was an overkill. But in terms of maybe hoping to start up economic activity, no, it wasn't an overkill. So it depends on the end goal.
So the system was a 100 kilowatt system,
No, this one was 25.
and you're sharing 25 kilowatts amongst about 100 homes.
Theoretically. When we did our calculations, it showed about 5 kilowatts. So, from the powerhouse, if you walk along the transmission line, so the first 5 houses were getting good light. The system is ready to have 20 volts. By the time we hit the middle section, the voltage dropped to around 100 volts. And the last house actually could not turn the lights on because the voltage was, the losses were so dramatic that power was actually not reaching them at all. So only part of the community was actually getting light.
We have another few minutes if anybody else has questions.
I have a comment. It's funny, when I think about local community development, I always think the community should be involved. And there's another project called Smart Cities, or Smart Communities as an initiative by IEEE. And they had a solar solution for Haiti. And they believe they have a good economic solution for Haiti. And they installed these systems for electricity, mostly addressing reliable electricity. And they thought that they trained the locals, trying to do the right thing. And one of the systems broke down, and it took a long time for it to get back up. And what they found was a lizard had crawled into the back of the fan, but no one had figured out that they should look, because they would look and there's nothing. So they pulled the system down, and the engineers from the project, you know, the overkill, trying to re-engineer, redo this. And one local says, well, why don't we just put some piece of material so there's nothing that can get in?
Yeah.
And it was all of $1. And I just thought, God, you know, so that it happens all the time.
Like for that system, they bought actually 2 transformers. One step up and one step down. They actually installed them reversed, so they had the step down in the powerhouse and the step up in the village. Now why did that happen? Because the engineer was a civil engineer and he told them to do that. So the community, when they installed the system, of course not going to work, and each transformer is about 150 kilos. So they moved that system on their backs from one place to the other. And when the engineer found out his mistake, the locals were with no way we're gonna transfer, and they actually dumped the transformers. So about $5,000 are just sitting, rusting on the rice fields.
Wow.
And when I visited, we opened it up. It was filled with, ants, bees,
Yeah.
snails. So that was $5,000 completely wasted
Wasted.
for no reason.
Yep.
Yeah.
Mahmoud, thank you very much.
Thank you.
I'm gonna try and stay on schedule here. We have about 5 minutes before our next session starts. So, if you'll, get a drink of water or take a few minutes to... Actually, no, we are actually on schedule, so... So our next paper is entitled Open Source Photovoltaic Systems Performance Modeling with Python. And the authors are Nathan Charles and Mahmoud Kabalan from Villanova University. Nathan, if you'll join us.
Thank you. Thank you very much.
So I have it open.
Oh, okay. All right, okay. Well, thank you very much. I'm Nathan Charles. I'll give you a little bit of an overview about what we're going to cover today. Just see if I can get this in a different format. Just gonna have to scroll through. So we're going to go with a little bit of the background and introduction to why this problem and why this work started. We're going to cover a little bit of theory, looking at the ephemeris, position of the sun, some irradiance and insolation modeling, then looking at sort of the PV module model, inverter model, and then the SolPy, which is the title of this open source tool, how the models interact. And then we'll look at a little bit of how the system is described for a typical model, and then using that to look at historic weather data and then compare an actual system that was model or performance to actual performance to the model using data from an internet source. So this work started in 2010 when I was working for Mennonite Central Committee in Bangladesh. There was a Sustainable Technology Research Center that I was working with. We were working with various forms of energy, primarily solar thermal